All right, so I'm Shri Bhupathi. I'm one of the founders of Mill5. We have a booth up here at 225 if you guys want to stop by, have any questions, or look at some demos that Jorge is going to be walking us through today. I've led several projects, across various industries, including capital markets, for AI and traditional software development, right? And this is Jorge.
Hey, hello everyone. My name is Jorge Gonzalez, senior engineer at Mill5, with larger experience working in AI, machine learning, software, enterprise software projects on the cloud and also at the edge.
Yeah, a little bit about Mill5. We're a global software consulting firm. We've done a lot of work in various industries. We do software consulting for traditional software development, AI, and machine learning. We've worked across, companies and enterprises in various geographies. We're headquartered in Boston, but we got offices in Medellin, in Colombia, Argentina, and in India as well. So if you got any questions, again, please, booth 225, and happy to answer those. Jorge is going to take it away.
All right.
Let me just.
So this is our agenda for today. We want to talk about a little bit how the new NVIDIA Ampere architecture will help you to split a GPU in up to 7 different GPU instances, and also how sparsity, that is also a new feature that the NVIDIA people put on their GPUs, will allow you to optimize your models. We're going to show a demo also, and we have a Jackson Irving device that we are happy to show you in our booth how it works. Okay. Well, we have different facts and challenges here. The first step is you may know that nowadays the new solutions, the new AI solutions require more than one model running at the same time. Not only 1, 2, 3, 5, right? So how you can guarantee when you introduce a new model in your solution, how you can guarantee that your system or your solution is still performing well? You need to be able to do that. Moreover, if you are in the cloud, you may know that cloud services are really expensive sometimes, especially when you are using GPUs. So in this case, you need to be aware about how you can, in some way, introduce some density on those GPUs and those services to be able to run more than one model in only one GPU and reduce costs. Also on the edge, if you think for example, in this kind of devices, those are smaller with less compute resources, less memory, and even less energy. So you need to take care of how do you optimize your models to be able to run on this kind of hardware. Okay, well, here the NVIDIA people created new brand chips, in this case the A100 GPU, that is optimized for enterprise AI and high-performance computing. Also, in that architecture, they introduced a new streaming multiprocessor and the third generation of Tensor cores. Right now, we are here to demonstrate how we can use multi-instance GPU. This is also a feature in the latest NVIDIA GPU architectures, and the sparsity. Right. Well, let's talk about multi-instance GPU. What is this one? Basically, we have the option on the, for example, A100 GPU to split your GPU in 7 different instances. That means that basically you have up to 7 GPUs in your system, each one with separated memory and separated compute. As I said, they are basically, we can see here, there are, if you have in your system 7 different GPU hardware. What is the benefit with that? We will have best quality of service, and you will have fault isolation. If a model or a workload that you have in the GPU will not affect any other workloads in the other instances that are running in the other instances. That means that you have predictable performance and latency. The cool thing about MIG is that it's transparent for your current applications. So you have CUDA applications, Docker containers, Kubernetes solutions. That will be transparent for you. You don't need to implement any code changes. That will be available for you right away. OK, for MIG, in this case, we are going to use the NVIDIA i100 4 GB of memory as an example. We have 8 different memory slices and 7 compute slices, right? So that will allow us to basically split our GPU in this way. Those are the profiles that are in some way predefined in the GPU. And we can create up to 7 instances with one compute slice and 1 memory slice. 3 with 2 compute, 2 with 3 compute. Those are like the base profile that we can use. There is an exception. You might think that if you create a 4 compute instance with 20 gigabytes, you might think that you can create another one with 3 compute instances are 20 gigabytes as well, but that is not available currently. So here's basically that we did with those slices. We have memory slices in the top, compute slices in the bottom, and you can basically create that vertical line to create a GPU instance. On the other side, you can combine those slices to create bigger instances, in this case, a 4G with 20 gigabytes instance. Cool. With this said, we are going to show you typical examples of how to use MIG. In this case, for training, we are going to demonstrate this in our demo in a few. But basically, during training, you may know that when you are experimenting with your models, you try to use different configurations of your neural network, introduce different hyperparameters. And that could take some time. And as you know, if you are in training an image classification model, a convolutional neural network, that will take some time. So here, MIG could help you to, in some way, parallelize those workloads. And at the same time, you are able to train different versions of your model. And for example, here, 3 different Docker containers using exactly the same configuration of the MIG instance. This will allow you also to, in some way, make sure that you are using exactly the same resources, and you will be able to compare those metrics that you get when you train the models. This is another good example. This is actually a architecture or topology that we are using on one of our clients. We have a computer vision model that is basically running real-time inference, right? We have an NLP model that is processing the same video stream for some voice processing, and we have 2 regression models. Here's a cool thing. You have exactly the same regression model here, but you could test a new version at the same time to do something that we call A/B testing or shadow testing. So that means that you are running the V1, that is your production model, and you have V2 that basically you are testing. Here, as I said before, on our client, we are running that computer inference, that real-time inference, sorry, in the host machine, just because we are using a frame grabber to get a 4K stream, 60 frames per second. And yeah, we need to be more near to the hardware. And at the same time, we have 3 Docker containers running the other models. This is the configuration that we are using. We have a MIG instance that is basically, we can say in some way that is the half of the GPU on running the AI inference, the real-time AI inference, and we have smaller GPU instances to run the other models. OK, I would like to say that all those implementations were created using CUDA 11. So I'm going to pass it on to Shri, that is going to talk about new CUDA 12 enhancements.
Yeah, thank you. So, so like Jorge was talking about, these are, CUDA 11 stuff. Those of you who've been following, the machine learning work space and, what's going on in that world, you'll probably hear or heard about CUDA 12, which is due sometime soon. I think the release is dated for March 2023. But just a refresher, the way HPC works or the way CUDA works is, you basically have a large workload, it's divvied up into smaller work streams, and those work streams are now sent out to different cores on your GPU, right? That's, like the traditional way of actually doing things. And, there are several threads that are working on each one of those workload, distributed packets and so on. What you've got with CUDA 12, however, is you already have a block of threads that's being supported by CUDA 11. The new construct here is a cluster of blocks, right? What this basically means is these blocks of threads are now boxed into a bigger box, right? Giving you a lot more performance. It gives you up to 16,000 threads per cluster that you can work with. You can actually get access to shared memory without creating multiple copies, right? And there's a lot of asynchronous stuff. There's actually a paper out there that talks about embarrassingly parallel asynchronous processing on the CUDA 12 Hopper CPUs, or GPUs, I'm sorry, right? So this is basically, the evolution of Moore's Law, right? CPUs with their architecture and stuff like that have been pretty contained. GPUs have taken it away, and with Hopper, I think NVIDIA is really setting the stage for massively parallel workloads, right? Some of the tests that we did to back some of that, some of those graphs that you see there, standard SVM models, right? You use it for classification and regression and such. We've seen about a 5 times better performance using the cluster of blocks on CUDA 12, and you'll actually see the other one is a pricing algo or a model. Without the cluster, so the cluster of blocks is something that is optional for you to start when you start coding, for you to opt into. If you're not using your cluster, you're about, or if you start using a cluster, you see about 2.7 times the performance gains out of this thing, right? So huge performance gains out of these things. If you want to see any of these or talk about this stuff, please come over. We've got the hardware and the software to kind of walk you through this stuff in our booth. But in the interest of time, I'm going to turn it over to Jorge, because he's got a demo as well that we're going to show you on the A100, right?
Yeah, A100. Okay, thank you, Shri. Let's switch to my laptop, please. I'm going to show you a demo. We have a VM running on Azure with an A100 GPU. So I'm going to basically demonstrate how you can run multiple workloads on that GPU. The first time I'm going to use only one instance to allow you. Are you able to see? Okay,
it's pretty good.
Okay, so the idea here is to demonstrate you that if you have only one GPU, if you introduce more workloads on your system, the other models will be affected by those new workloads. And after that, we are going to configure the similar architecture that we showed you during the presentation for training 3 different instances exactly with the same configuration and show you how it works. So I'm going to start now. As you can see here, we have a NVIDIA A100 GPU running on Azure, 80 gigabytes of memory. Right now, we don't have any MIG device configured on the system. And as you can see here, the MIG is enabled, right, on the system. You might need to know that by default it's not enabled, so you will need to run the specific command on the system to enable MIG on your GPU. So let's go to create an instance. In this case, I'm going to create. Okay, let me show you first which are the available instances. Remember the table that I showed you before? We have these different configurations out of the box. So we have up to 7, 1G, 10 gigabytes of memory instance. And each configuration is showing us how many instances we can create, right? So let me create this one. That is basically the entire GPU So let me run this command really quick. OK, our instance is created right now. So I show you our system. We have a GPU instance right now, an MIG device, like a separate instance with 80 gigabytes. So what we're going to do now is I'm going to start a container that I have already configured in my system that is going to basically start a workload in the system. So let me go here. There you go. So this is a trivial model. It's running on TensorFlow. As you can see here, we are using the world GPU, MIG 7G 80 gigabytes, right? And it's running faster, right? So it's taking 11 seconds, 10 seconds. I'm going to start a new workload. Right? It's a different container with a different configuration of the same neural network. Let's finish this epoch just to see that it's consistently getting 10, 9 seconds per epoch. If I start this other workload on the same GPU, of course, you will see that this is going to run slowly after start the new workload. Let's see how it works. Right now we have two. Let me show you here. We have two processes running. This is a small model, basically 2,000 megabytes of memory, something like that. But all those processes are running on the same GPU, same instance. And yeah, you can see here we start to getting 2 seconds of delay in our process. Let me kick off the third one. Got it. So this tier 1 model is going to introduce more latency in our system. So let's see how it works. As you can see, each workload started to run slowly, more slowly. Yeah, 14 seconds in this epoch. So you might understand here that yeah, each workload that you added to the GPU in a single instance is going to affect each other, basically because they are competing for the same hardware, for the same memory bandwidth. Cool. With this said, I'm going to stop these containers right away. I'm going to configure. Let's wait for the stop. Okay, one stop, two stop, just stop. Great. Let's confirm that. We don't have nothing running in the system. Okay. I'm going to reset the GPU in order to be able to configure a new instance. Here, if I show you right now, we have one instance running, and we don't have available instances because we are using the entire GPU. I'm going to reset the GPU right now. It's important to mention that the configuration of the MIG is not persistent. I mean, if you reboot the system, you reboot the device, you will need to reconfigure your topology. It's not persistent in the system. So I'm going to show you again that we don't have nothing configured, no MIG devices found. Let me switch to the other screen. And here, I'm going to create a different topology. I'm going to create 3 different GPU instances with the same configuration. Let me show you right away. Okay, I created 3 different instances, two computer slices, 20 gigabytes of memory each one. Let me show you here. We have 3 MIG devices on our hardware, right?
So what you've done here is really take that one GPU and slice it up.
Exactly. For three separate hardware GPUs.
Awesome.
Exactly. So I'm going to kick off exactly the same Docker containers with the same workloads. I'm going to start the first one. And you will see that right now it is using this instance, right? Device 0, that means that I'm using the first GPU instance, right? It's running. It's not faster than with the whole GPU, because remember, we are using a slice of the GPU. But you will see during the demo that the performance is always the same. It's predictable. Okay, I'm going to kick off the second one. Let's allow finish another epoch, just to show you. Let's start this one. Okay, let me show you that those are running in different GPU instance. We have ID3, ID5, ID6, and the memory is used in different GPUs. Your process is showing you in which instance is running. So nothing happened here. Notice that same 14 seconds every time, right? Let's see how this workload performs before we start the third one. Okay, let me kick off the third one. Cool. As you can see here, nothing happened. 14 seconds every time. So that is predictable performance. In production, that will allow you to, you will make sure that nothing happens if you introduce a new model using this kind of hardware. Cool. Yeah, let's switch again to a presentation, please. Cool. I want to mention the other feature. Unfortunately, we don't have time to demonstrate how sparsity works here, but we are happy to show you in our booth how it works on these kind of devices. But faster sparsity is basically a new feature that NVIDIA introduced in their GPUs to, in some way, be able to improve the performance in 2x, basically reducing the network model size. How it works, we eliminate directly from the network, from the neural network connections or weights that are near to 0 or 0. Basically, we remove it from the neural network. We remove the connection or even the neurons. We do that maintaining the model accuracy. That is important, of course. And that also allows us to run efficiently in hardware. These devices are small, so you need to consume less memory if possible. There are some techniques to basically apply sparsity. There are pruning techniques. You put 0 the weights, you remove entire part of the neural network. We can talk about that in our booth, but yeah, that is everything that we have to show you today. As I said before, happy to show you what we have in our booth. We only have 1 minute. If you have any questions, happy to answer them. No? OK. Thank you so much for your time.
All right.